Now take some gate question. A sine wave Vp equals to 1.536 volt and 128 levels, gate zone 3. Calculate output noise power. Output noise power is 1 by 12 del equals to twice mp upon L. If peak value is given to us, means del equals to Vp upon L. 1.36 square upon L, 128 square. 1 by 12 into 1 point into 1.536 divided by 128 into 128. Cancel out these terms. 1.2 1.2 into 10 to the power minus 6 minus 4. Cancel with this, minus 5. Now result is 10 to the power minus 6. 5 volt. Now we will discuss the DPCM, differential pulse code modulation. In DPCM, we are, instead of transmitting complete sample in a cycle, in PCM we are transmitting complete sample in a cycle. Instead of transmitting complete sample, we are now transmitting a difference between two samples, because in PCM we are considering the each encoded sample is independent to each other. There is no correlation. Practically there is lot of correlation between practical signals are video signal, audio signal, voice signal. Practically in all signals there are correlation between adjacent nearby samples. To use these correlation, we are now transmit difference between two successive sample. For transmission of difference between two successive sample, we have to add memory element in the PCM device. So the basic block diagram of, and via this scheme we reduce the redundancy, and uh, we we are saving number of bits. Instead of complete cycle, we are saving number of bits in a particular cycle. If bits are saving, means we are saving bandwidth. Block diagram for DPCM is, we construct DPCM transmitter and receiver. Receiver is lower portion of the transmitter. We transmit MK. MK means sample value. MK transmit, and then previous value of MK. If I mark this sample as MK, previous quantized value of MK is marked here, MQK. Cap means previous value. Difference between these two value is DK. MK minus MQK, this component is mod, maybe either direction difference. DK, after quantization, this DK is quantized, means Q. We use Q. This is sample value, analog type. This is digital now. This DK is accumulating previous value, and now it is current value. predictor predict previous value is modify and next cycle is coming. This is the complete cycle. We mark everything. This difference is known as dk. After passing through quantization, dqk transmit, and at the transmitter we receive this component and arrange in this way. If we add previous value and current value, result is DPCM is not much useful for us. In particular case of DPCM is very useful for us. Benefit of DPCM is the quantization noise in DPCM reduced by the factor dp upon mp. In previous case we are transmitting mp. In current case we are transmitting dk. Maximum value of difference means dpk. In the previous case we are transmitting mp. In this case we are transmitting only difference, peak difference. So the noise is reduced by the factor mp upon dp square, and snr is improved by the same factor. For this purpose we are using memory element in PCM. So in DPCM, a particular case of DPCM which is delta modulation is very useful for us. Particular case is 1 bit DPCM is known as delta modulation. Delta modulation. Delta modulation is very important topic in gate. Sample correlation is further exploited by oversampling around 4fs or 5fs the baseband signal, and the sample are transmitted with difference amount with DPSK scheme, because DM is a specific case of 1 bit DPSK DPCM. DM is a specific case of 1 bit DPCM. 1 bit DPCM means number of level is 2, number of bit required is 1. We are sampling in this case corresponding sample in this case difference amount with 2 level and number of bit is 1 on the cost of oversampling. Bandwidth required is reduced because formula for bandwidth is n fs by 2. Formula for bitrate is nfs. Here we took value of n is fs by 2, value of n is 1 fs. Bitrate is fs. Fs is not Nyquist rate here. It is 4 and 5 time of 4 and 5 time of Nyquist rate. 4 and 5 time of Nyquist rate NR. So on the cost of oversampling we achieve delta modulation. Basic block diagram of delta modulation is draw basic block diagram of delta modulator. When a message signal MT is applied on it and previous value of message signal is this. This block is known as comparator. Comparator have two type of decision, either plus E or minus E, and this is called samplers switch which sample the value at fs rate. Integrator amplifier for accumulation purpose, for memory purpose, and demodulator. DM demodulator. The basic idea for DM is construct a sine wave. We want to transmit sine wave through this idea, comparator and sampler. For transmission sine wave through this, we sample sine wave in a cycle in 4 sample. Assume in a cycle we assume there are 4 sample. When we apply message signal here, then if initial value of message is 0, then compare with 0, put 0 value, result is plus d. Result is plus d. Plus d compare uh, plus d value, some positive value is applied to comparator, result will be plus e or minus e. Obvious result, if d is positive, plus e result. Comparator jump to plus e. Plus e value sample, plus e value sample, and we got one pulse, and this is goes to accumulator, and accumulator count is plus e now. Then current sample value is this one. This compare with plus e. Again d is positive. D positive, obvious choice of computer is jump to again plus e. Plus e sample, again compare, again plus e. In this way we get 4 sample. After that, when the accumulator count is 3, after that again compare with current value. Now decision is minus d. In the case of minus d, comparator jump to minus e. Comparator jump to minus e. So in this case we get result is minus e. Minus e sample here, and in accumulator minus e. Now current value of accumulator is plus 2e. Plus 2e compare with next value, and in this way complete message signal is tracked by steps plus e or minus e. Either of the steps plus e or minus e, we get the result. In case comparator output is 0, in case error detector output at this juncture d equals to 0, 0 is applied to the comparator. Now comparator is confused. If it is positive, plus e, negative, minus e, 0, it is confused. Either jump to plus e or minus e, either direction. So it might be jump plus e or minus e, depends. If jump to plus e means this much of error added to the signal. Jump to minus e means this much of error added to the system, means maximum error in DM is plus minus del. So result is, in demodulation side, this step size is arranged accordingly. If increasing order, then we are making steps, and decreasing, and we are making in decreasing step, and again increasing and decreasing. So we can approximate the message signal by our available step size. So in this way we knew quantization error. In this case we can calculate quantization noise power is. Quantization noise power we will calculate. In delta modulation we knew error is in the range of plus minus del to plus del. Function PDF function is defined in this way: 1 by del plus minus del, otherwise 0. 1 by 2 del minus del. Noise power is x square by solving this expression we get del square by 3. Now noise power will increase. We are using now everything optimum condition, means minimum number of level, minimum number of bit on the cost of sampling. So noise power raised by 4 time in previous case, but total noise power is spread uniformly over the bandwidth fs. Power within bandwidth b is b upon fs. So noise power is modified due to this factor, because noise within noise is uniformly spread, del square by 3 uniformly spread within the power complete bandwidth. Effective bandwidth is b upon fs, because here uh, fs is not Nyquist frequency. So we multiply this factor to get actual noise power. Signal to noise ratio, from here we can calculate signal to noise ratio 3fs m square upon del square b. Final SNR is 3fs m square del square b. Two type of error generated in delta modulation: slope overload error and granular noise. Slope overload error and granular noise. Granular noise. Slope overload error, fast varying signal, or granular noise for slow varying signal. How can we identify slope overload and granular noise? Is slope overload for fast varying signal. Fast varying signal. What is this? Slope overload error is one, if signal have larger slope, higher slope, then it's known as slope overload error. This is due to if step size is, in DM we are following some step size, slope of the step size is lower than slope of the message signal, then slope overload error occur. We are not following the original message signal. To follow original message signal we have to increase step size. We have to increase step size. Increment in step size is only solution to overcome the slope overload error. Slope overload error due to, reason is that because this line ts sampling time difference 1 by fs sampling time, sample sam difference between the sample is sampling time. Slope of the delta modulator slope is step size upon ts, should be maybe should be For slope overload will occur. To slope overload occur, slope of the modulator should be less than message signal slope of message signal maximum. If it is so, means slope overload occur. If it is reverse or equal, critical condition. Case 1, slope overload occur in the case of slope of the modulator is less than message signal slope. If it is equal, means optimum condition, no problem occur. Optimum condition. Optimum condition. In optimum condition, slope of the message and slope of modulator are equal. Solution of the slope overload error is to increase step size. By increasing step size, our problem is solved. Problem arises due to fast varying slope. Variation of the slope is very fast. Means slope means tan theta and is very high. Signal is fast varying means with small fraction of time amplitude change in amplitude is very large. Fast variation means small fraction of time amplitude variation is very large is called fast varying signal. In optimum condition everything okay, no slope overload occur, no error occur. Case third. In case third, if slope of the modulator is greater than message signal slope, maximum slope of the message signal, this type of error is known as granular noise due to slow varying signal with large span of time, small amplitude variation. Means amplitude variation within the step size. Amplitude variation within the step size. Opposite polarity pulses on the application of slow varying signal. Yeah, small variation in signal. Very small slope. Almost DC. Almost constant signal is applied to modulator. Opposite polarity pulses is answer. This is known as granular noise. Granular noise. Solution for this problem is reduce the step size. If we reduce the step size, signal may follow small variation in the signal. Reduce the step size. For slope overload, increase step size. For granular noise, reduce step size. We have to compromise one of the two front, either reduce or increase. Discuss one question regarding slope overload. Which of the following signal can be applied to delta modulator whose step size is given to us and sampling frequency also. Condition is no slope overload occur. No slope overload will occur. Fs of t greater than mt dash max. No slope overload means slope of the step size is greater than maximum slope of the message signal. If applied input are A 2 sine 1200 by t, B slope of sine wave is am cos omega mt, Maximum slope of is am omega m 2 pi am fm. Then we can write slope of all these masses 2 into 1200 pi 1 into 26 pi 3 into 1000 pi 4 into 400 pi. We can rewrite in this way. I write here 2.4 k pi 2.6 k pi 3 k pi 1.6 k pi. To maintain a slope, formula is m empty dash. Empty dash is available to us of optimum value del upon ts del fs. 0.1 into 2 pi k 20 pi k 2 pi k is our answer. If any value less than 2 pi k is our answer. Fourth one. Fourth one is our answer. Any value less than 2 pi k, in that condition no slope overload will take place.